randomness, I think the only thing that you can do is stick to first principles and keep playing. And in the long run, even if it's a random function, if you have at least 1% more chances of winning than losing, but if you keep playing long enough and stick to those first principles, then I think you have a higher chance at succeeding. And on the other side, if those principles that help you solve the problem that you think is the most important, then even if you don't succeed in some sort of social metric, the path is going to be at least fun. And you know this is a PhD student or just a researcher.
All right. So, hello and welcome everyone to whosoever is tuning into this particular podcast. Today, I have Max Mergenthaler Canseco with me. Max is the CEO and co founder of Nixtla, where he's developing highly accurate forecasting models using time series data and deep learning techniques, which developers can later use to build their own version of the pipelines. Max is a self taught programmer and researcher with a lot of experience building things from scratch. So, Max, welcome to the podcast.
Thank you, Jay. It's so good to be here. I'm very excited about this interview.
Yeah. So, what was your entry point in AI? Like, what was like, can you walk us through your background before you started dabbling around AI models and programming?
Yes, absolutely, Jay. I started messing around with code and programming before AI was called AI, and we called it machine learning. And maybe even before, when machine learning at the very beginning, or many machine learning practitioners, or what we would be called machine learning practitioners, were actually data scientists. So I remember back, it was probably 15 years ago, when the whole concept of massive online education began with two platforms, edX and Coursera. And I remember taking one of the first classes, Introduction to Python, in edX. Back in the day, there were only 3 courses in edX. I think now there are probably tens of thousands of courses. And that's how I started teaching myself how to program, and that's also when I started developing a very keen interest for data science and machine learning models.
Right, right. And was it like apart from all of these courses, were these the only resources that you resorted to learn these machine learning techniques, or like was it like research papers? Like, what was the set of resources that you found to be most useful?
It was an interesting mix. So I think, as many of my contemporaries, one of the first systematic approaches that we got to machine learning was the Andrew and G course, Intro to Machine Learning, where everything was still written in Octave, not even MATLAB or Python. And I remember studying that course and resolving the exercises, and that definitely gave me a very a good introduction to basic concepts like gradient descent and the difference between supervised and unsupervised learning. And I remember I had come across those concepts before, but I remember Andrew and G being specifically clear, and I remember the course very being very well taught and very practical. So that was one aspect of it. And then on the other side, I was good friends with different researchers that were doing either econometrics or machine learning or even empirical psychology. As you remember, I did some research at the Max Planck back in the day, where we were doing some empirical behavioral economics research, or experimental psychology, if you will. And also the discussions with them and reading papers with them together was very important in developing a more solid understanding of basic machine learning concepts, but also seeing what other people were trying to achieve back in the day with different techniques and different experiments.
Makes sense. And so, like, can you walk us through this journey? So now you are the CEO and co-founder of Nixtla. So can you introduce what Nixtla is like, and how did you transition from a person who is learning the fundamentals of machine learning from, like you said, like Andrew Ng courses to almost finding a problem? Like, how did you find this problem, and how did you go about of building this expertise? Because from for most people who might not know you, you help develop like some of the biggest open source libraries. Like I think they have been getting a lot of attraction from developers and also researchers. So how did this transition happen from a person learning the fundamentals all the way to making a very notable contribution?
Thank you so much. Um, I think in my particular case, and then again, this is just an individual data point, which shouldn't allow us to extrapolate without further data points. But in my particular case, I think the thread that unites my very eclectic life is curiosity on the one side, and on the other side, the passion or the willingness or the necessity to solve problems. Like I get curious about problems and then I try solving that. And I think that's at least also I have seen other people that share that intuition. I think that's a very interesting driver in developing different careers. So in my case, I started studying philosophy. I was very passionate about those fundamental questions, and very rapidly I grew interested into what's called analytical philosophy, which is the branch of philosophy that is more involved with science, logic, even a philosophy of mathematics, philosophy of physics. And from there, the switch to programming wasn't that hard, as at the end of the day, programming is nothing else but a structured sequence of steps, of logical steps. And and then I think what's very interesting about machine learning, data science back in the day is that it is a field that was composed of many different fields. So on the one side, you have the statistical tradition. On the other side, you have the computer science tradition. But then, of course, on the other side, you also have the domain specific tradition, which is where you apply machine learning methods to solve problems. And back in the day, I started growing very interested in solving practical problems. I led different research groups at the Mexican government, inside the government, inside the Trade and Promotion Agency. And then at some point, my other like passion, which was curiosity, started becoming more present. So I decided to start experimenting with the concept of funding startups, and that's how it started. And then after many different startups, Nixtla was grown. And if you want, we can speak more about that.
Yeah, definitely. I would like to learn more about like how did you find out a problem? Because like once I think people who start working with AI and research, like there are so many problems one can identify, right? Because at the end, AI or machine learning algorithms, they can, if given right amount of data, can do miraculous things. So one thing I wanted to learn is, I'm sure you must have stuck across many different kind of problems that you can solve using your expertise, right? So how did you figure out this particular problem? That how did you figure out there was a market fit? There's an application that some people would be interested in developing it further. Like how did that intuition happen?
Yes, it probably didn't happen. So I was working on these problems because I was interested in this problem. So maybe let me make a meta commentary before answering your direct question. I firmly believe that it is very hard, maybe even impossible, to beforehand choose what problem is going to become interesting, what problem is going to become sexy, what field of science is going to become mainstream, and which field of science is going to be forgotten. I think that the best thing that we have as researchers, as humans, is to pick up what we like the most. So in that sense, I think the most important and the most interesting problems are the ones that are ultimately the most important and most interesting for you, because that's going to give you the most important ingredient of all, which is perseverance and passion to solve that problem. Everything else is completely up to chance. Everything else is at the end of the day a probabilistic function that we don't know how to resolve. That being said, obviously, I think there are problems that are at least um, impactful in an immediate way. And in my case, the Nixtla was founded by me, Azul, and Christian. And Azul and Christian are both mathematicians and econometricians. And I myself am a professional philosopher by training. But we realized that one of the main questions that was shared across disciplines is namely, how do we quantify uncertainty? How do we develop different quantitative methods to try to forecast the future based on past behavior? And on the one side, on the philosophical side, this is, of course, very well studied, from the Delphi oraculus to modern philosophy of uncertainty and decision under and other uncertainty. That was a pressing question. But on the other side, econometricians were the ones that built the time series forecasting field back in the 60s with important models such as ARIMA and the whole box Schultz algorithms. And we were very interested in trying to on the intellectual side, on trying to understand more about the time series algorithms and how to improve the field. But on the other side, we were very interested in a practical problem. Back in the day, we were working at a demand forecasting startup. We were trying to forecast different sales of many thousands of products in a retail company, and we found that the existing technologies in Python were not sufficient. So we tried developing our own libraries and made that an open source package. And that open source package started getting a lot of traction. And then we switched to becoming to making this a startup, to making this a company. And it was very interesting because we saw back to machine learning and statistics, we saw in the whole field of time series, we saw a lot of polemics between classical statistics, machine learning, and now even deep learning methods. So that's also something very interesting.
Right. And I think one thing I wanted to probe you further is, and even on the offline call that we had, you mentioned something about that time series prediction also has its roots in behavioral economics and quantitative psychology. Like, correct me if I'm wrong, if I'm butchering the names, but can you give us, like, most of the people who are listening to this podcast have background in computer science, and they understand time series prediction, like stock market prediction or house prices prediction. So these are like bunch of numbers that have some patterns over historical time figures. But can you explain, like, in a very, like, maybe give us an analogy of like how it ties back to behavioral economics and psychology? Like, how is time series in some ways dependent on that?
Absolutely, yeah. It's not directly related. It's personally related in my case. I started some of my quantitative work back in Berlin, where we were writing a paper talking about what's called decisions under uncertainty. And in the decisions under uncertainty, which is nothing else as how people make decisions when they don't know the full picture, there are two classical paradigms. The ones is the description based decision making and the experience made decision making. And description means that someone gives you like a classical description of the problem. Let's say you can choose option A, which is certain 100% certainty. I give you $3, or option B, I give you $4 with an 80% probability. And that's how you would phrase an experiment of decision under uncertainty with that description. On the other side, you could let people sample from two machines, machine A and machine B, and every time they click the button of A, they will get $3, and every time they click on B, they sometimes 80% of the times they would get $4, and 20% of the time they would get $0. So if you do the simple math, the expected value of B is bigger than A. So rationally speaking, if we optimize utility, we should be choosing B over A every single time. That's not the case. That's not how people work when you give them a description of the problem. And this is the classical Kahneman argument against utility in economics, that people are not rational because they are risk averse. But then on the experiment side, something interesting happens, namely people tend to act more rational. What happens at the end of the day is that they obviously sample. When they click A, they see 3, and when they click 3B a couple of times, they see 4. So they believe that B is maybe always or more often 4, so they choose 4. Nevertheless, long explanation is we were studying how that experience description gap comes to be, and we were making a commentary on the whole field that has been a very well studied thing in experimental psychology. But that's when I started thinking a lot about how to think about uncertainty, and not only uncertainty about the present, but uncertainty about the future. Namely, how is the stock market going to behave? How many items am I going to be selling next week? How many people are going to be attending the parade, etc., or how many people are going to be using the subway? And at the end of the day, I believe that in certain cases, time series algorithms, time series forecasting methods that, of course, have different ways of quantifying uncertainty, like, for example, with conformal prediction or different prediction intervals or multi-quantile predictions. Those sorts of methods give us an interesting way of thinking about possible futures that we think are more likely to occur based on our best knowledge today. So that's a relation between my personal relationship between my thinking about uncertainty when I was working in Berlin, and also my thinking about uncertainty when I was doing philosophy, and now trying to generate algorithms that are being used by many different big companies in the world to try to optimize their different problems.
Wow, this is very interesting because I didn't. So, like, as a computer science person, or like more like an engineer, we don't have that much understanding of what is the grounding of these kind of methods, like a structure, like you said, like Kahneman and uncertainty. We don't have background into that. And I'm very curious, like, since you have been working in this field for long, implementing models that can do the prediction, and I'm sure you have tried out a bunch of architectures like transformers or even higher versions of that. I'm curious, like, have you found if these models are inherently good at capturing these kind of uncertainty and making much multivariate predictions, because there are multiple factors that on go, right? Like you said, we don't expect people to be rational, versus in some cases it would be depending on the sampling that you do. So I am like, can you tell us more about, like, I'll ask a two-phase question. So first is, how did you use, like, did you happen to use any of your prior experience into designing the architecture? And if that is the case, how like, what are your comments on the current versions of developments in the AI? Are those architectures good enough?
Yeah, that's a very interesting question, and I'm gonna try to improvise a brief story and commentary on the time series field. So probably the first time series algorithms that we have, or time series methods, are what we call now the seasonal naive, which is to forecast next Thursday. You look at and the samples of last and Thursdays, right? And then you can do different things, like even just the last one, or some sort of aggregation of a set of prior Thursdays. And we see those algorithms like back when Egyptians were trying to measure the tides of the Nile. They were like marking sticks, and then you could see, okay, last year we had this, so probably this good year is going to be similar. And that algorithm, funny enough, the seasonal naive, is still one of the best time series algorithms that you can use in many different cases. And of course, on an aggregate level, this is because time series are very hard to predict. So sometimes taking just the last value works fine, also because it's extremely easy and extremely cheap computationally. And then we have a very long story of mathematics and stuff. And probably the next big appearance of time series algorithms per se, disregarding, of course, harmonic series and Fourier series and all those important trigonometric approximations of signals. But in the mid 20th century, we see a lot again 20th century again a rise of like people trying to predict the future based on the past, and then we see the emergence of very solid econometric techniques, algorithms like the ARIMAs, uh, and different like econometric routes that were based on basically statistical traditions. What's great about those algorithms is that they have an intuitive interpretation. Those can be somehow decomposed into trend, seasonality, and that gives us somehow an understanding. Okay, this is going up, and this is maybe repeating itself. And those two words are the main components of the time series vocabulary: trend and seasonality. Then fast forward, the whole machine learning explosion happens, and people start using things like grading, boosting trees, like XGBoost, like GPM, and they start seeing some interesting advantages, namely with, for example, an ARIMA. If you have to train one ARIMA for all your series, that means if you have 100,000 products, you have to train 100,000 ARIMAs, and then of course you have to find the specific values of the ARIMAs, which starts to become more and more complicated. With global models in like GPM and XGBoost, you can train one model for all your different series, which can be computationally easier. On the other side, it might be easier to find like the optimal models given all the different advancements that we had in the machine learning field. And then after some time, the whole deep learning revolution happened, and people started using neural networks into trying to, for time series, LSTMs, different RNNs, of course, deep neural networks. Some people even tried and explored like adversarial networks and evolutionary algorithms. Those two didn't turn out to be very, very good for our field. And now, or a couple of years ago, people started using transformers for time series. And something very interesting happened. In all the other fields, computer vision, natural language, it was clear, absolutely clear, that transformers and first machine learning and then neural networks, and then transformers were the absolute best architecture that we could have right now. And you started seeing things like GPT-3 outperforming every single thing that we had before. And we started seeing those very interesting scaling laws where more compute and more data brought far better results. With time series, something different happened. During the last, I would say, 5 years or so, people have been still debating, do we need transformers? Do we need deep learning in time series, or are statistical methods enough? And we have contributed to that debate. We have shown that you can outperform very sophisticated architectures, even very sophisticated products out there with very simple statistical methods, both in accuracy and in efficiency. So we have shown, like, we have a very interesting experiment that you can replicate on GitHub where we showed that an ensemble of simple statistical methods can outperform some of the most sophisticated, like, auto forecasting techniques of what was offered back then by Amazon. And this thing cost a lot more, and this thing cost a lot less. And this is completely open source, and this other Amazon thing not. But then we and a lot of different researchers started thinking, why is that happening? Why is it so that in our field there isn't a clear winning of these very interesting architectures? Is it because maybe, as you were hinting, the data is inherently differently? Is it because the structures are differently? And I think we had a very interesting insight, namely that it was not about the model, but about the data. And then if you see the difference of data sizes for training data and evaluation data in other fields and in our field, the biggest competitions in our field, in the time series field, were data sets that had like 100,000 series, right? So it's very small data compared to the millions or billions of images that you have in ImageNet or in other classical benchmark data sets from computer vision and natural language. So we did something interesting, or at least I think it was interesting. Namely, we said, what if we could try to prove that those scaling laws really exist? What if we could create the biggest data set of time series that we could find, and then train a very big transformer or different transformer architectures and try to have this foundation model? And that's how TimeGPT came to be. So at the beginning, we were skeptical, is this going to work? Is this not going to work? But it worked. We showed that by training a large transformer and doing zero-shot inference, you could outperform many of the statistical machine learning and deep learning SOTA methods. And this is very important, without training, like on a new data set, on a complete new data set, what's called zero-shot inference. And after we published, many different research labs also like supported this finding, and many different research labs have been publishing foundation models for time series. Google has published, Amazon has published, Salesforce, ServiceNow. So IBM, I also think, has one paper. So I think now we're starting to see that the very long answer to your very short question is that, yes, I do believe that transformers are an optimal method in time series for foundational models, assuming you have enough data and assuming you have enough computational power.
Yeah, no, definitely. I mean, I love the answer and the justification behind that, because we like I primarily work on medical imaging data sets. And when the whole vision transformer thing came, right, like that was the big boom where everybody wanted to understand if VITs are really gonna be better than CNNs, because when it happened, people had access to big data sets. Like ImageNet itself is a very big data set where the people started replicating these numbers. And when like I was very curious, because if you consider like ResNet was kind of the benchmark vision model, and people were trying to benchmark those numbers on top of that. And I asked my professor, can I just try a vision transformer? And we had like a very small data set, which it's a high dimensional data set compared to ImageNet, but the number of samples is still very small. And we saw some very bad results, and I was like very confused, like, am I doing some implementation that is wrong? Why are people getting consistently good performance using vision transformer networks? And the answer is what you hinted towards. Given enough amount of data samples, transformers are really good at. But if you have like a data lack in your data sets, or like the number of samples are not great enough, then I think CNNs kind of tend to be, at least in the vision field, CNNs kind of relate to the benchmark. So like maybe a follow-up question for that is, like, was that the only finding that you found out, that if given a good amount of data samples, transformers can do well? But if you have like very limited number of samples, and if zero shot is not the end goal, then you might have to resort back to the existing statistical models before GPT models.
Yeah, I think this new evolution of foundation models in time series opens the door to very exciting possibilities. So right now, if you want to do time series forecasting, you need to have the expertise of doing it. Like this is similar to before. If you wanted to do NLP, you had to train your own models on your own data or some public data sets and then deploy it inside your company or your research lab to use it. Now you can do stuff out of the box with GPT or with the cloud or with the different Mistral models or Anthropic models. I don't favor any of those companies particularly. Um, and I think that changed the world, or a small portion in the world, in a very interesting sense, namely that now very sophisticated NLP and computer vision technology is available out of the box for researchers, engineers, and business people. And we're trying to do the same for time series forecasting. So with TimeGPT, we have a model that is pre-trained and that can be now consumed out of the box through an API, or you can deploy it inside your own infrastructure, which means that now you can start doing very sophisticated, very efficient forecasting without the need of training your own models. So in the same way that the LLMs companies and LLMs approaches have solved the problem of not everyone having the expertise and not everyone having enough data to train their own models. We are contributing with other research labs to solving the problem of people not having enough time series and people not having enough expertise or computing power to train their own transformers. So I do believe that in the future, most people doing time series are going to be using foundation models built by someone else. And maybe they're going to fine tune in their own data. And for some very specific cases, they might train their own models. But I think the future is in foundational models. And this is very, very interesting, because I think what we have shown and what other research labs are starting to show is that there is indeed something like an underlying structure of that's shared across different time series, across different domains. I really like how the Amazon research lab puts it. They created a model called Chronos, and they call this the grammar of time series, hinting to a like ordered structure that can be, of course, studied and deciphered. And in the same way that language has a structure and therefore can be predicted, it seems that time series have also something that we could call a structure and that can be learned with enough data. And of course, it's not only about the amount of data, but the diversity of the data and 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 an architecture that is able to learn that. So yes.
Right. And one thing you said, because you kind of basically provided this foundation model, and you said because data set was small enough, like how did you go about getting more data sets? Was it just like acquiring data set, or did you look into synthetic data generation for training these models? Like, well, like how did you fix this data set problem in the first place?
Yeah, the first thing that we did, and I think that's what set us apart other research labs, is that we went for the easy solution, which is maybe the hard solution, but we started scraping the internet. so so we started collecting all publicly available data sets that we knew we could use for training from different domains: IoT, healthcare, economics, finance, electricity, retail. And we created this very big data set, and we started training and testing on that data set. For the next versions, we are also exploring synthetic data generation, and I think that's a promising or interesting avenue. And recently, we have seen other researchers. I think 2 weeks ago, a new paper came out where they are using images to train a time series model, and they are showing very good and interesting results. So it seems that I still have to study, and we still have to replicate the results of the paper, but it's an interesting idea that you can like somehow extrapolate the structure of image into a time series, and then learn that time series with or that time series pattern with your algorithm, and then predict new time series, not only from a different domain, like not only from electricity to finance, but from images to electricity to finance, which is quite interesting.
Wow. So are they like trying to understand what is the like what exactly does these images contain? Do they have like lots of numbers, or like they are trying to extract like
No,
what do
no,
these images have?
they were training on ImageNet, like random images, and then
Wow.
somehow the transformation of those images to time series, and then the training renders interesting results. So this is a new result from some of the interesting labs in the world. I think this was part of Salesforce and some Chinese universities. So that's also very interesting.
Hmm. And one question that I had when while you were trying to say a few things is like one question that I always had is like GPT models are basically autoregressive models, right? So one thing that I saw some time back is like whenever you use Chat GPT, let's say, if you ask it a very difficult mathematical question, it will stutter a lot because they will because inherently it doesn't understand the concept of numbers versus text, right? Because it is trying to memorize few things and then blurb it out into the output. Like I want to understand like what kind of modifications did you make in the time GPT where it can specifically understand numbers as what it is, so that it can understand the mathematical reasoning or logic behind these numbers rather than just doing an auto regression on all of these text tokens.
Yeah, the main difference, we call it time GPT because it's a pre-trained transformer, and one could argue is generative. Um, but the main difference is of all the models that I have mentioned, maybe with exception of one, uh, the models are being trained on a very specific loss function. They are trying to do forecasting, time series forecasting, and only time series forecasting. So you can't pass any text, or we haven't passed any text, but I don't think it's gonna work like at all. It's just gonna it's trying to predict the next sequence of numbers or values based on the past, but it's not tokenizing in the same way that LLMs are tokenizing a text and trying to predict the next sequence of tokens to create a coherent as a set of sentences or even mathematical equations. So that's the main difference. It's not an LLM. It only works for time series and time series only. So it's not smart in that sense that it speaks and understands and maybe even pretends to reason. On the other side, I think LLMs and foundational models don't understand anything in that sense. They don't understand
Right.
numbers. As when you mentioned like, do they understand numbers? I've started to think, what are even numbers? Like, you have the integers, and then you have the rationals, and then you have the irrationals, and some of those are constructed by the others, and then you have the irrationals. Are they like, do they even exist? Like, people spend dissertations arguing if the rationals exist or not, and are they just a construct? So I don't know I think there's an interesting question around what does it mean for an algorithm and or for a person to understand what a number or what a word is, and in which respect are the new technologies coming closer and closer or not to that thing that we call understanding.
Right, right, right. And one follow-up question for that is, like, if you see most of these large language models that have been trained on huge corpora of text, like you said, scraped from the internet, right? And typically people are amazed by their performances because most of the times, like this is a well-known joke on the internet where you say test data set is basically the trained data set, right? Because you are testing out it's trained on almost all of the human knowledge available. So even if you interact with it, it will give you some output that seems magical to us. But you did mention that when you are training these data sets on scraped data sets, you are able to do zero shot inference, right? So you can use these foundation models on a data set that it has never seen before. Let's say I have a startup and I want to use this particular product for prediction over there. What do you think is the intuition behind the time GPT or on the models that you are developing? How are they able to generalize these numbers better? Because technically, the pattern that I'm using, I'm trying to predict, it has never seen before, right? So what makes it generalize so well?
Yes, that's a very interesting question, and the underlying intuition is that there is such thing as a shared structure across different data sets. So to give you a like a very simple and false analogy, but that helps that hopefully will help make me my point is if you see at the patterns of let's say mm, sales of a specific retailer, you're gonna see that on Sundays some of those retailers many go to zero because they don't open their stores, and that on Fridays you see always a high point, and that Tuesdays are normally like related to Tuesdays, and then you have like what we call like a very seasonal time series, right? And then if you somehow saw the electricity consumption of that same store, it would have a very similar pattern. So,
Mm.
or maybe it is the same, but one day before. Because let's assume that before the people come, like you have to replenish all the shelves, and therefore you have to have more people. So it's the same time series, but shifted one to the left. One. So what I'm trying to say here is that again, like things like seasonality, trends, special events, those patterns are shared across different domains, and therefore, if you have a diverse enough and large enough data set, the model can start to learn, okay, how is the future going to look like based on the past? And at the end of the day, it's in that sense, it's a problem that can be generalized the same way that language generalizes. No, it's it's impressive, but at the end of the day, we're very predictable in how we speak and how we reason and how we say things, at least most of the times, because people have said it like that before or similar that before. So it's
Yeah.
in the same way that we are not truly unique in some aspect, time series aren't truly unique in one aspect. Of course, there's always the unpredictability and the weird stuff, that the hallucinations, if you want, that LLMs have. Mhm.
Yeah.
And obviously, our algorithms too, they sometimes hallucinate and go crazy and predict things that weren't even seen before. Like you have like a series here, and then you have values very up or very down, and that's obviously wrong, right?
And I'm curious what you think of one of the recent models that came out of Google that they introduced in the Math Olympiad competition. I don't know if you followed those news, but Google announced a specific model that they made it compete in the Math International Math Olympiad competition. And I think I need to double check, but I think they came in second. Like I'm interested, like because since you're developing a large model, I won't say language model, but like a large time model. I'm curious, like, what you think if these kind of huge architectures can truly capture the nature of complex mathematical functions, and what's the way forward? Like, do you think they would be able to get mathematical intuitions much better than humans? Because even like cracking international Olympiad, like just on a bunch of few data sets and few GPU times, is like questioning. It's like the AlphaGo moment, right? For the mathematical community.
Yeah, I haven't read the paper, and I'm not following this news, but I think it's a very interesting problem, and I think what you mentioned regarding AlphaGo and LLMs is very interesting, because I think those are two fundamentally different approaches on solving intelligence or reasoning or consciousness or whatever you want to call it. I don't like the word consciousness. I think it's too inflationary, but on the one side, AlphaGo was trying, at the end of the day, to play a game. It's an algorithm that is trying to minimize like a loss function that is based on winning and losing. And LLMs, as you mentioned, are autoregressive token predictions that don't really like optimize for winning and losing. So I think like trying to bring those two worlds together, it's a very exciting, very interesting idea. That being said, I don't know, like from what I have read, most of the mathematical like solving problems are more about like manipulation of symbols rather than forecasting like values. So I think there is still a big way. So what I'm trying to say is I still think that the field is like diverse, and there are many like different bubbles, like LLMs on one side, AlphaGo, or those sort of algorithms on the other side. We have foundational time series models here. You have other specialized models there. And then obviously at some point, if someone manages to bring all of those together, that's that's going to be a very interesting and cool thing to play with.
I definitely agree. I definitely agree. And one other question that I had is, you also, like, before I think that time GPT came in, you also have a very large contribution given to a model hierarchy that does the hierarchical interpolation for time series forecasting, right? Can you speak to a little bit on that? Like, how did that tie in? Like, is it like somewhat related to what time GPT is trying to do, or in a very different sense? What is the architecture differences between these two models and the applications that they are targeting?
Yes, absolutely. So we published a paper called the N hits, and the N hits was our attempt to help to reconcile the statistical or traditional methods and the deep learning methods in the time series field. So uh, we followed on a tradition that was started by some of the people of the Joshua Bengio lab. One very smart and very important person in our career called Boris Oreshkin. He published a paper called the NVIDs, and the NVIDs was one of the first neural network models in time series that could be decomposed into interpretable structures like seasonalities and trends. And we really like that decomposability or interpretability because it was closer to our upbringing as econometricians or mathematicians. And that's the NHITS. And the NHITS is basically an interesting expansion of the NBITS that uh, came to be when we start thinking about forecasting long horizons, forecasting the distant future. And one could say that the further something is in the future, the harder it is to forecast. And if someone says that, it would be right. And formally speaking, this is so because if you forecast like one step at a time, then you start concatenating errors. You start like deviating more and more to the up or to the down of the graph by concatenating the errors. And then on the other side, what you could try to do is forecast the whole thing at once and not do that like recursive or sequential prediction, but that is very expensive, computationally speaking. So we said, okay, what if we could somehow mix the two? What if we could forecast everything at once, but instead of forecasting all values, we just forecast all odd numbers. So we forecast the first value and the third value and the fifth value, and then we interpolate in those between those values. Or what if we forecast every, like, I don't know, or could build the algorithm every prime number, and then we interpolate or whatever. So that's where the hierarchical intuition comes from, that you can split a time series between different lengths of numbers that you are predicting and then interpolating. And by doing so, you have or you can combine what we call the multi-rate signal sampling and then the hierarchical interpolation techniques. And that combined with the NVIDIA architecture that I mentioned before of Oreshkin is basically the NHITs. So it's very different, and it's a complete different problem that what GPT is doing, what ChatGPT or other LLMs are doing. But it's very interesting because it gives you, it's a very accurate algorithm. It's a very robust algorithm, but it's also an algorithm that can be decomposed into different stacks that somehow resemble the classical intuitions of time series decomposition into trend and seasonality. So that's the idea behind the NHITs, which was mainly developed by Christian, my co-founder, but Azul also had very important contributions there, and a former colleague called Kim.
Wow, very interesting. And like I was, yeah, because I'm like while you were trying to explain this, like I was almost lost into one of the other applications that I'm trying to develop for my PhD, and I was almost thought like if I could like maybe read this paper in detail to understand like if I could use this, because we are trying to improve the super resolution project
Mhm.
for medical imaging. And since you were mentioning something about interpolation, and I was like maybe I could think something along those lines. It's not directly for like the one that you are suggesting is not directly for imaging, but I thought like maybe in theory this is possible. So yeah, thanks for sharing that. Like at least this is like just for me,
Mhm.
it gave me a new tangent to something interesting that I can explore.
It's interesting. Yeah, one would assume that if one pixel like is completely white and the other pixel is completely black, the middle should be something in between, right?
Exactly, exactly. And one of the other challenging things that in our data sets is like we work with PET scans, right? So PET scans have a
Mhm.
very small intensity range, and when you're trying to upsample, even like a small voxel change indicates a different disease. Like so, we are talking about at the scale of like 1 millimeter. And the problem, like for most of these models nowadays, since they are trying to upsample at a very different rate, they tend to miss this. So whenever I'm trying to upsample, it's like you can imagine it's like an average effect for the whole data set. And like if I just average the brain structure, it has nothing to do with your brain structure if I use that at test time. So it's very interesting. These models work completely fine when you're trying to reconstruct a zebra image or a giraffe image or something else, because the resolution is not that great. But when we talk about medical imaging, it really comes down to the very specific accuracy at the voxel 1 millimeter scale. So yeah, just a thought. Like yeah, I mean, I'll maybe give that a shot. Like maybe it won't work, but at least something interesting I'm trying to explore. And thanks for giving that tangent.
Absolutely, it's a pleasure. Tell me
And
what comes out of it.
I'll definitely, I'll definitely do that. Yes. And one last question before we wrap up the whole time series part and jump to a few other questions that I have for you. I want to understand, like, if there is a person who is trying to listen to this podcast and has no understanding of like how these so complicated models are being used for time series prediction, what would you say? Because you have been developing these tools and also you have open sources, so I'm pretty sure a lot of people are trying to use your model into their application. So you do interact with them. What kind of over promises versus under promises you see from these applications? What are the things that you think you would put it out for people that, hey, why aren't you guys using these models for this? It has immense amount of potential. Because I think one nice thing that came out of any kind of GPT models is the application domains increased a lot. People are using these models for tasks that people have not thought about. So what are the kind of things that people you think are interesting applications of these models?
Yes. So um, I think one thing that a lot of people try to do is to use this for financial applications, namely the classical idea trying to forecast the market. And it's interesting because in some respect, the time series field, back when the econometricians were doing it, started somehow as trying to model the stock market, and it worked very well at the beginning, and then the market incorporated it and it didn't work so well afterwards. That being said, we are seeing some people using us in financial settings. And I think one of the secrets for, and this is one of the like secrets that everyone knows, is that it's not only about the algorithms, it's also about all the data that you have. So obviously very interesting hedge funds and quant firms have sophisticated algorithms. They might use our algorithms or not. but they have other privileged data. So I think finance is an interesting domain with the caveat that data is important. One thing before I start talking about TimeGPT use cases, it's important to mention that we are like very open to people using our commercial product, which is TimeGPT, but also using all of our open source algorithms. And there in the Nixtla verse, we have built many different libraries that include classical statistical methods, that include machine learning methods, neural forecasting methods, also what's called hierarchical reconciliation methods. So we have a very wide, and we like to believe the most comprehensive open source time series ecosystem that can be used by everyone without paying anything. It's MIT, so everyone can use it. And then we have this thing called TimeGPT, which is the pre-trained thing, the commercial version of it. And for someone that is new to like the whole time series field, but might be interesting in using TimeGPT, I think it's going to become evident to them once they hear that you can do now forecasting out of the box without training your own infrastructure, the different use cases that you could be doing. And this is something based on my or our personal experience at Nixtla. We're starting to see use cases that we never thought of before, like people are exploring if they could predict circadian rhythms of cattle so they sleep better or they predict better how much they're going to grow. People are trying to, of course, classical things, predict electricity demand to like do optimal charging batteries when they are cheap and selling the energy when it's expensive. But also we're seeing smaller and smaller startups adopting our technology to build on top of it. So they are creating new use cases for supply chain, for retail, for different domains. So at the end of the day, what we believe is that time series are the DNA of the world. So in the same way that we communicate through words, systems, businesses, institutions, they communicate through data. And most of that data is time series data. So we do think that everything from like the hot dog stand or the pretzel stand in New York to the biggest bank in Shanghai are time series based. And obviously the bank is probably doing some sort of time series algorithms, I would like to believe. But the hot dog stand isn't. But they should. They should be forecasting the most accurate way of seeing how much product should I buy for the next week so it doesn't go bad and I don't lose any sales opportunities. And now we do believe that in the future with foundation models, these people are going to be able to also have access to state-of-the-art technology. So what I'm trying to say is, and it's always very hard because people ask us like, what are the most important use cases? And we think it's the whole world. Like we see the whole world as time series.
Anything that has numbers is a potential application. So yeah.
numbers and dates, because it's just numbers. There's probably a better algorithm.
Right, right. And one of the other key things that I really think is very interesting, and as a researcher, I really value that is like you guys being open source, right? So you have developed like the whole development phase for at least these two models, the NHITS and TimeGPT. You guys have open sourced it for developers, and most of the part is being interpreted, like people can understand really what is the proposition for you guys. So I wanted to like, I mean I know the answer to my question over here, but I wanted you to comment more on the on top of this is what are the pros and cons of open sourcing these tools, because nowadays we see huge companies who are not trying to open source versus there are companies like Meta who have been very open about the llama models. So like are there any pros and cons? Maybe there are some cons of open sourcing it, and maybe you are on a better stance to maybe explain on this. So what kind of things have you realized, like have you any time understood like there are some cons to open sourcing these new technologies?
Yes. Thank you for the question, Jay. So it's important to mention TimeGPT is closed source still, at least. So the NHITS is completely open source, and all the other libraries that we have built are completely open source. And TimeGPT was built on top of our open source. So someone with enough time, expertise, data, and compute could build TimeGPT out of our open source. Um, and then maybe I can answer the question: why didn't we open source TimeGPT? And for us, it was a strategical decision. We at the time we were a startup of maybe 5 people, and we knew we were competing in a race against the top research labs in the world, and the biggest tech companies in the world. So we wanted to keep our moat as long as possible, and not share our secrets with those very big labs. And I think it paid off in the sense that we were acknowledged as the first company to public a foundation model, and also the first company to make it available for the public to use as an API. So I think the cons of open sourcing is that it might, of course, give your secrets away. But I do believe that open source is the future, and we at Nixtla are very interested in open sourcing it. We just have to find a way of how do we open source this before we lose some competitive advantage. It's interesting to see that other research labs in our field have open sourced their models. Those research labs are Amazon, IBM, Salesforce. So I I think it's easier to open source your IP when you're a $1 trillion company
Yeah.
than when you are like a smaller startup. And that being said, I mean, internally, we love open source. We have built upon of open source. We use open source. We think it's the future. We do believe you can build a business on top of open source. So we're thinking about different how to manage this. But for us, like at Nixtla, we have like a creed that identify what we are. And one of the things that we have is that we think our like utility function, or what we are trying to build with the business, is not to generate revenue for the shareholders, but we believe the definition of business, or at least from Nixtla, is to maximize value for our users, customers, and colleagues. And users are the open source users. So we do believe a lot in contributing to the community, because the community contributes back, because it's a synergy. It's like science. It's the only way of going forward, right?
Right. Yeah, definitely. I think it was, I think maybe a year back or so, where people trying to there was a debate on internet, right? Like as in people who were not very much pro into open sourcing were afraid like how this would be used by people. And like if you see like correctly, so I think in maybe 1 year or 2 years there have been so many applications. People have access to these hugely trained models, and they have been using it in all different ways. So it's very hard to keep a check. Versus if you also see open source, like the Llama, like the whole Llama family has been developed so nicely. There are people who are trying to merge, like you said, the community gives back. There are so many nice papers coming out of the mentioning the limitations versus pros of these tools. So, but yeah, I mean, I think even regardless of that, like you guys have done a great job at making these things accessible to developers. So definitely kudos for that. And I completely understand there should be at least some competitive advantage to be taken away, because you're still developing at a very small scale. So it definitely will help you boost. So yeah, thanks a lot for doing that. And well, one towards the end of the podcast, maybe I want to zoom out on you also, like as in like I wanted to understand, because a lot of people nowadays are building applications using these large language models, and you have a long history of developing things from scratch. At least, like correct me if I'm wrong, but you had two other startups, at least two other startups where you tried to build a few of the ideas that you already had. What are the kind of insights that you learned from that? Like is it like what kind of intuitions you think made Nixla much more bigger than those ones? Like what were the kind of mindset shifts that were happening in your head during those times? And what have you learned in this process of building things from scratch over and over again?
Just that's an interesting question. And one of the things that I believe is that those sort of questions are complicated and very prone to narrative bias and to selection bias. So I'm always very skeptical when I hear people telling about, okay, what did we do right and what would we do wrong? Because at the end of the day, is you don't know. You didn't run the counterfactual scenarios, and you build a nice story and you select the memories that better suit your narrative. But at the end of the day, it's very hard to understand. Okay, what's truly it's a like casual multivariate problem where many things contributed. That being said, I what I'm trying to hint at is that There's always a very big random component on how things turned out to be. And the other thing that I'm trying to say, it's probably never about the individual. It's nothing. It's not really about me. And now I'm speaking here, but it's definitely about my co-founders, Christian, Azul. It's definitely about the people that we were surrounded with, about our teachers, about the different people that we could interact with, and if you hold such a like a random or random prone position where you believe that success or failure is determined at least in some important degree out of randomness, I think the only thing that you can do is stick to first principles and keep playing. And in the long run, even if it's a random function, if you have at least 1% more chances of winning than losing, if you keep playing, you're going to lose a lot. And that brings us back to my experiment when I was researching at the Max Planck. But if you keep playing long enough and stick to those first principles, then I think you have a higher chance at succeeding. And on the other side, if those principles are really, as I was mentioning at the beginning of the podcast, principles that help you solve the problem that you think is the most important, then even if you don't succeed in some sort of social metric, the path is going to be at least fun. And you know, this is a PhD student and as a researcher, like it's extremely hard. Research is extremely tiresome. It's hard. Like most of the times you don't get the results that you want, and most of the times you maybe don't publish because you didn't prove what you wanted to prove, or you didn't find what you wanted to find. So I think the only secret there is, okay, then maximize also for the present, namely maximize for the joy that it brings you to struggle every day. And I think that's what's different maybe at Nixtla than the different companies, that I love trying to solve this problem. I love giving to the community, getting things from the community. I love how we are making an impact in the world. I love the people that I'm working with. So I would like to believe that that makes me more motivated to work, and the more motivated I am to work, the better the possibility of the outcomes.
Yeah, definitely. I love the answer, and like I'm just trying to reflect back on most of the people that I've interviewed and interacted with in real life, and most of the times, like when something really sticks out from that person, like we normally like for example, if I were to look at your profile, I really I would see that these are the open source projects, and that what I would associate it with your success. But most of the time, it's like your love for just building things, like no matter what, like it just happened that and hits was picked up by developers, and TimeGPT was also picked up by people who really showed interest. But at the end, you guys just wanted to build something that you guys had core interest and expertise in. So most of the times that goes unnoticed. But like I'm pretty sure, like if NHITS or TimeGPT didn't work, you would have been working on something else that was in your pipeline, and that would have been a fair shot. So yeah, it's like you said, the first principles, figuring out those first principles is very important. Seeing what drives you. So yeah, thanks for the answer. And one last question that I have for closing this interview is, most of the people, again, like I interact with a lot of bunch of students who are trying to listen to this podcast, and when I entered AI, it was already a very cluttered field, right? Like I started in 2020 or 2019, where it was already like big shots and big companies were already publishing deep models. And nowadays, with large language models, we have lesser access and lesser ability to train these models, but still the AI field keeps on evolving. What kind of advice you would give to young researchers or developers who are trying to understand the hype versus reality of AI nowadays? What do you think is like maybe not like I think if you follow Jan LeCun, he said at one of the conferences that if you're a student or an academic researcher, working on large language models is not an optimum pathway, because it's an oversaturated field. You don't have resources, and the scope for research is very less. Maybe he said it from a very good standpoint. He didn't want to discourage people, but like just having access to bigger GPUs is not a reality if you're in a university. What kind of advice you would give in your position to understand the hype versus reality of AI nowadays?
Yeah. Maybe like a self-contradictory claim. Don't follow the advice that I'm gonna give you next because probably I'm wrong.
Yeah.
Nevertheless, it's very interesting. We collaborate with academia, and we have seen and a lot of different academic researchers, and we know the struggle. It's on the one side, I mean, we like to think about things abstractly, no? And at the end of the day, you are playing a game in the sense that you are trying to maximize a utility function or somehow define a winning losing scenario. And it's weird because it's not clear which game academics are playing. Are you trying to publish as much as possible and then get tenure? Probably not, at least not in machine learning, not in computer science, given that industry pays a lot more. Okay, so maybe in that case, you are not trying to optimize for publication numbers, but publication plus internships, and then getting a good offer at a big firm. And if that's the case, that you should definitely play it differently. But maybe you are optimizing for something else. So it's weird. And I think at the end of the day, you should have certain clarity on what you want if you want to pursue that goal. Like if you want to go to industry, then you have to play a very different game, namely try to understand what the industry is doing and maybe not be the most innovative ever, but try to be a very like good contributor to the research labs that they are building. If you got to go academia, it's another thing. And then, of course, you have the specific question about like, should I go with the hype and try to do LLMs, or should I go like different things? And it's clear that Jan LeCun would say something like, "Don't study LLMs," because he has his own approach against like LLMs, and all his research people are building upon that. Like he's not a person; he's a whole research institution. I know how many papers he has co-authored in the last year alone. Like so I guess my advice would be in that sense, what I'm trying to build upon is probably there isn't a wrong or right answer. Probably nobody knows what's good. And maybe if you work on LLMs, you will find something very interesting with low effort and you don't need high GPUs, and then you will get thousands of citations or be hired by a very important firm. Maybe you won't. And in that sense, I think the best option that you have again is to stick what you really like the most and become an expert at that. And I mean, I'm very biased because I come from a field that is like very unpopular, very unsexy. Nobody gets famous in philosophy. Nobody gets like offered millions of dollars to work at Amazon as a philosopher. Uh, but I do think that fundamental work is important. I do like the stories about the mathematical intuitions that nobody like thought were important, and suddenly they were used for new fields of physics and revolutionized the whole thing. So I even neural networks, right? People were like writing about these things many years ago, and nobody like was paying attention because they were like just two neurons and not like
Yeah.
millions of neurons in the web. So I think my advice is assuming, and that I believe this is true, but assuming that you cannot know for sure which is the optimal path to success because you don't know what's going to happen next, and because the things are crowded and very complicated, stick to do what you like the most and become very good at it. And if you become very good at it, there's going to be a place for you in the world.
Yeah. I I love this advice. Think I really like the like words because one thing that is really standing out in this field of AI is the kind of like I was a very I would say neutral slash pessimistic person when large language models came out because of understanding like how used data sets were and how inefficient if you see the models are if you have like 175 billion parameters, and I was expecting something magical. But now on top of this, like since there are a lot of people who are focusing their efforts on developing a better version of these models, I think transformer was like just the backbone. So it really, like you said, like the opportunities can be endless. There could be new things that really pop up, and you have to really keep on exploring, like just keep on hitting the wall until something clicks. So yeah, I love the advice, and you guys are a fantastic example for that. You guys developed something that came out as a passion project, and now it's fully funded and people are finding it useful. So yeah, thanks a lot for sharing all this information. I think we got to cover a lot more about who you are, like how did you founded Nixtla, what are the kind of applications that you guys are targeting, and like what kind of products you guys have built. We also try to understand what are the challenges previous to the products that you guys developed, what were the challenges in time series prediction, few things that even I learned myself. So thanks for sharing that. I am pretty sure people who are listening will also find this useful. But I'll also leave a link to all the awesome projects that you guys have built that which are open sourced, and also I'll leave a link to your profile because I really find your profile to be really interesting. You have been doing some great work, so thanks for doing that. And again, thanks for being on the podcast.
Thank you so much, Jay, for having us here. Thank you, of course, to the people listening to us and to everyone listening. We're always very happy to help you with your time series problems. So please use or try the open source. If you don't want to code everything yourself, feel welcome to use TimeGPT. Everyone has a 30-day free trial, so you can test it for free and do whatever you want. And also, if you want to talk about something else, please contact us. And maybe one last thing that I would like to say, Jay, and this is very important for us at Nixtla, is that uh, we believe I mentioned diversity as being a fundamental aspect in training models and making them more accurate, but we also believe that diversity is a very important aspect in building a company and in academia. And we encourage and always feel very happy that we are like a company that was founded by Mexicans and members of the LGBTQ community. So we are always very happy about endorsing diversity and encourage everyone to do the same and keep the field and keep both your data sets and the field diverse.
Yeah. No, I love that. I love that. Absolutely. Thanks for that.